Okay, so we're at the start of a new week, the second half of the second 6 weeks. Just a few things before we go ahead and get started. We are going to wrap up the notes today, but on Thursday the 18th, you have a quiz over this material. Okay, the homework that I'm going to go ahead and give you today, which is due Wednesday, by the way. I'll go ahead and give you a couple days on that. The big one is next week. Next Thursday is going to be your second exam. It'll definitely have what we've talked about up to this point as far as trig goes. After this week, we're going to move into what's called the law of sines and law of cosines. I don't think we'll have that on the test because I'm pretty sure we won't be able to finish it before next Thursday. Because also what's happening Monday. Yeah, you guys get the day off because we go to content focus sessions. So you'll have a 3-day weekend this weekend. So that's coming up. You got a quiz on Thursday, an exam next Thursday, the 25th. And this is what we've been currently talking about. The past couple of days I've seen you, Connor.
Will the quiz have applications on it?
I put a word problem on there, yeah.
Okay.
Mm-hmm. And will. And I'm going to be more lenient on the quiz. I'm going to have probably some information on the board to kind of help you through the quiz, but by the time the test rolls around, then I'm going to, require that you know that material, like the formulas and all the conversions and all that good stuff. Okay, basically this stuff right here. We started talking about arc length, which is just a portion of the circumference, the complete distance around the circle. S, the arc length, is equal to the radius times theta. Theta's got to be in radians. Now, when we're talking about circular motion, that had two parts to it, what we called angular velocity and linear velocity. Angular velocity is the rate at which the angle is increasing with respect to time. How fast is it rotating with respect to time? And we always started these problems the same way. We have the number of revolutions over time, and we like our angular velocity to be in radians, so we go ahead and multiply it by this familiar fraction, 2 pi radians over 1 revolution. The first thing that should always cancel is the revolutions. So then you'll have radians per time. That's your angular velocity. And you'll notice we have the omega Greek letter here, that symbol for our variable. Now, what do I do with the angular velocity if I want linear? All I have to do is multiply it by the radius that I have. Okay, as soon as you do that, you've got linear because this introduces a unit of measure, whether it's millimeters, inches, whatever that case is. So that means we don't need the radians anymore. So now it's a length with respect to time. And we use V to go ahead and represent the linear speed. So linear speed is the actual speed that an object is moving in a circular path. Yes, sir. We like them to be in radians, yes, because we're going to associate that with a unit of measure. And we can't do that with degrees. Okay. So this is what we have been talking about. And before we go ahead and move on, I did write this up before school today. So for those folks who did come in this morning and participate in that problem challenge, thank you so much. I really appreciate that. If you didn't, hopefully maybe you still looked at the problem, kind of look. But here's what I did. I looked at the problem and tried to determine what the angle was for an entire day. You'll notice the problem said you're given the second hand is 20 inches per minute. Well, that's a measurement per time, so they're providing you the linear velocity. So we know that in order to get the linear velocity, you just multiply the radius by your angular velocity. So I just kind of worked backwards to figure out what my angular velocity is. So I got 5.88235 radians per minute. Now, why am I saying that's slow? There you go. What is 1 full revolution? There you go. Satish says 6.28, right? Because that's 2 pi. So I know that the 5.88 being less than that 6.281 revolution, well, it's got to be running slow. So it should be running this number of radians. Okay, 24 times 60, that's the total number of minutes in a day, times 2 pi, the number of revolutions. Well, what I did was I took the speed at which it should be going, that 24 times 60 times 2 pi radians, and you'll notice I subtracted the product 24 times 60. See, it's still the minutes in the day, but the partial revolution that it was getting, okay, the omega that I'd solved for previously. Well, that difference right there gave me 577.19 radians in a day, and then I just started to change it from there. I divided that specifically by 2 pi, to get the number of revolutions. Okay. Now, this is still going to be recorded in minutes, so it's going to take close to 92 minutes that you're losing per day with this particular clock. And then I just went ahead and divided by 60 to give myself the hours. Okay. So some people had it in terms of the number of seconds, which was really close to 5,500. Some people gave me the minutes, some people gave me the hours, and all those were fine. Okay. But there we go. How many people who didn't come in still took a look at the problem? Okay. So did we get it right? Okay. Good. All right. But again, thanks to those folks who came in. That went really well. Okay, we got 4 problems left, and we are done with these notes. Okay, so I've only got 1 problem on area of a sector. It's very straightforward. It's just plugging into the formula, simplifying, and you're good. And then the rest of these are going to go back to arc length. All right, so here's how I find the area of a sector. It's 1/2 times the radius squared times theta. Now, just like arc length, theta has to what? Be in radians, not degrees. And we're not talking about the mode of your calculator. Okay, you can still work with radians and degrees and have it in degree mode. We're not ready yet to put it in radian mode. We will very quickly. But let's take a look at our example. Find the area of the sector of a circle of radius 2 feet formed by an angle of 50 degrees. Round to 2 decimal places. Okay, so let's say we have our circle here with a radius of 2 feet. All right. There we go. So let's say 50 degrees is going to be like this. So it's not like before. We're not trying to find the arc length associated with that central angle. We're trying to find the area of that sector. So a portion of the full circle's area. Okay. Well, do we have the radius? We do. Do we have theta? Yes, but we need to convert him because it's always got to be in radians. So let's see here, 50 degrees over 1. What is the conversion for that? Okay, pi over 180. Pi over 180 degrees, because notice the degrees cancel. These are also divisible by 10. So it looks to me like we have 5 pi over 18 radians. Okay, and from here, it's just substituting right in. Area is always 1/2 times the radius squared. Well, 2 squared is going to give me 4. And then we're going to multiply it by theta, 5 pi over 18 radians. And again, we know 1/2 of 4 is 2, but I just wanted to show the substitution. In fact, when I go ahead and plug it in the calculator now, I am just going to go ahead and type 2, parentheses, 5 pi over 18. So how many square feet roughly am I looking at? Okay, about 1.75 square feet. That's it. That's all there is. There we go. Okay. Anybody have questions? Not sure where something came from. Easy. Okay, well, let's take a look at number 8. This is a pretty nice little problem. I like this one. It says Memphis, Tennessee is located at 35 degrees 9. What's that little tick mark? Minutes. Okay. North latitude of New Orleans, Louisiana. Okay, which is at 29 degrees 57 minutes north latitude. Assuming that the radius of the Earth is 3,960 miles and the cities lie along the same longitude, find the distance between the 2 cities. Now, are the longitude, are those the horizontal or the vertical?
Wraparound boys.
The wraparound boys.
Yeah.
Never heard of them put like that, but they do wrap around the Earth. That is true. They are the vertical curved segments. Yes. Okay, so this kind of problem, I always encourage people, if there's not a picture, go ahead and draw one. So what do we call it if we start our rotation on the positive x-axis with the vertex at the origin? Remember, that's standard position. Okay, so we've got 2 angle measures here. The first one is going to go to New Orleans, so I'm just going to go ahead and put an in here. Now, If you want, we can do this, but I'm going to show you how I did it. We know that because this is in degrees, minutes, seconds, it's going to be 29 point something degrees. Okay, so that right there is the measure for New Orleans. And then we have Memphis, Tennessee, which is further north. So let's say I'm going to put M for the Memphis. And this second longer arrow, that would represent the 35 point, whatever measurement we have in the degrees there. Okay. So imagine through these we have a circle kind of going through the whole thing here. And what we're trying to find is the distance between the cities. I want that arc length. Okay, so this isn't area of a sector anymore. Okay, what was the arc length formula again? I forget. S equals what? Okay, so S is equal to the radius, times theta. So here's the thing. Here's the theta that I would need. So how can I find that? There we go. Okay, Connor was saying the same thing. Satish had that. We want to subtract the 2, but then we're going to have to what? Convert it to radians, because remember, the formula has to be in radians. All right, so here's how I did this. 35 degrees. So you remember, if you choose this button here between 9 and the open book catalog, gives you this whole menu here. So the second row, the second item, the one that's already highlighted. That provides you a fill in the blank for degrees, minutes, seconds. Okay. And what was it? 35 degrees, 9 minutes? And you don't have to put in 0, but I'm going to go ahead and do so anyway. See, I'm going to go ahead and convert this to decimal degrees as I take the difference. Or you could find the decimal degrees and then subtract them. That's completely up to you. But I'm going to go ahead and subtract. Now do the same thing. And I think the other one was 2957. Is that right? Okay. All right. So all I'm going to do is subtract the 2 DMSs, and it'll convert it at the same time. Now, I went ahead and gave me a fraction because of my settings, but 26 fifths is what? 5.2, 5 1/5. That's exactly right. So we're looking at about 5.2 degrees. Okay, but as Aiden said a moment ago, we need to go ahead and make sure that's in radians. Okay, so theta is equal to, I'm going to take the 26 fifths times, what is it again to make radians? Pi over 180. Okay. So let's see here. So I'm just going to go ahead and multiply the previous answer times, oops, I hit myself, pi over 180. So I'm getting about 0.091 radians measured between them. Would you guys agree? I'll take that as a yes. Okay. So now, what was the radius that I was provided? The 3,960, right? Okay. So the arc length, the distance between the two cities, would be the 3,960 miles times the 0.091 radians that we just got. Now, see, I went ahead and rounded it so that I could actually write the value on my paper and, again, show my work. But in the calculator, I can use that exact value to multiply by the 3,960. Okay. So I'd say we're looking at about 359.4 miles. Okay. Is that what you folks are getting? Okay. So about 359.4 miles. Boom. Okay. And there, I believe there's a question like that on your assignment, very similar to it. Okay, questions? All right, well, we got 2 left. And let me go back to this one for just one quick second. Is everybody okay why we're looking at the distance between the two cities as a curved distance and not just a straight line as you would like on a map? Is everybody okay with that fact? Do we need to elaborate? Okay, I'm not saying anything, so okay. If you do want to ask me about it later, just let me. Okay, 2 questions left. Some earthly discoveries. Compute the length in feet of an angle measure of 1 minute on the Earth, given that the radius of the Earth is 3,960 miles. Okay. So does anybody think way back a couple weeks ago to when I first introduced DMS, what is 1 degree equal to? How many minutes? 60 minutes. Okay, so 1 degree is going to equal 60 minutes. Now, what the question is asking, let's say you have a point on the Earth, and the Earth is constantly rotating, right? It's spinning. Well, what it's saying is, in 1 minute, how far is that going to spin in the minute in feet? We're talking about the arc length on the surface of the Earth. Oh, I'm sorry. I was just saying if you're paying attention and can't put anything past Aiden. Okay. So yes, 1 degree is 60 minutes. All right, so you ready to try one on your own? Okay. The only thing here that you're going to have to do, you're still using this formula. Do we have the radius? We have the radius, so we have half of what we need. We just have to make sure that we have theta in radians. So you'll have to convert that. Okay, so while you guys are taking a look at that, and bounce ideas off each other or, help somebody if they're having an issue, I'm going to pass out your assignment. Here we go. Did you get an extra? Oh, yeah, there's nobody sitting behind me. Go. Okay. Okay. Is there anybody confident enough you think you've already got the final answer? Aiden, you think you got it? What you got? Okay. A little high. I will tell you, I'm looking for an answer in the 6,000s. Okay. Susie, is that what you got? No? Okay. 4146. Closer. Okay. Well, let's go ahead and walk through it. The only thing we need to change is theta, right? So right now, we've got 1 minute. Okay. But because of the ratio, well, wouldn't that just be 1/60th of a degree? Okay. Imagine if I were to solve that over there, the 1 degree equals 60 minutes for just the 1 minute, that would be 1/60th of a degree, right? So now I'm going to multiply that by pi over 180. The degrees cancel. Now, if I remember correctly, I want to say that's 10,800 is what I got, right? Okay. So pi over 10,800. Okay, so that's the radians. So now that I want to go ahead and plug that into the formula. So the arc length S is equal to the 3,960 miles times the pi over 10,800 radians. And of course, remember, once you introduce a unit of measure, the radians just kind of disappear. So let's see what I'm getting. 3,000, was it 960? Times control divide, I got pi over 10,800. Okay. Now, hold on a second. I said that my answer was like in the 6,000s. What is this? Remember, in miles. The problem wanted feet. Okay, so did everybody get at least the 1.2? Okay, good. There we go. So now if I've got what we have here, like 1.2 miles, well, how do I change that to feet? Multiply by 5,280. Because there's 5,280 feet in 1 mile. So I'm getting about 6,082 feet that the Earth is going to rotate from a point to when it stops a minute later. Okay. Hayden, so do you see what happened, or? Oh, okay. Okay, there we go. So about 6,082 feet. Good. And there we go. Now, we can go ahead and do the exact same thing for 9b. What's the length of an angle of 1 second on the Earth? So a point on the Earth in exactly 1 second, what's the arc length that it's going to rotate? Okay. Now, I'm sure someone's already thinking of something a lot easier, which is a really good idea. You can go ahead and run it through the same thing. What's the conversion for degrees to seconds? 1 degree equals what? 3,600 seconds, right? So you could do this the exact same way. If in 1 minute, that's 1/60th of a degree, then 1 second would be what? So that would be 1/3600th of a degree, right? Just like before, I could divide through. And then I would go ahead and multiply this by, again, your pi over 180. And then multiply that outcome by your 3960. But does anybody know what's that shortcut that I was referring to? Because the previous problem was doing what? 1 minute. Now we're doing 1 second. Oh, not multiply by 60. Divide by 60. If you take your previous answer and divide by 60, you'll get the exact same answer that you would down here. Okay. So I'll go ahead and start there just to show that, we're going to be correct. So the 6,082 feet from the previous problem, I'm going to go ahead and divide by 60. So in 1 second, we're looking at about 101 feet. Now let's see if we get the exact same thing if we run through using the formula. All right. So let's see here. I don't remember what that was off the top of my head. Let's see here. 648,000. So pi over 648,000 radians. The 3,600 times the 180. Okay, degrees cancel. So now I'm going to go ahead and take the arc length is the 3960 miles times the number of radians. Pi over 648,000 radians. And remember, now that we have a unit of measurement, the radians are gone. So let's see here. 3960, parentheses, control divide, pi over, what, 648,000. Okay. Now remember, this is still in what? Miles. So about 0.02 miles, not very far at all. So just like on the last one, I'm going to convert it to feet by multiplying by 5,280. And isn't that exactly what we got just a moment ago? Okay. Was anybody thinking about that shortcut? Okay. Xavier, you were? So you already had the answer? Nice. Okay. All right. Does anybody have any questions? Anybody not sure where something came from? Okay, good. And we have just over 15 minutes for you to go ahead and start working on your assignment. So I tried to make sure you have as much time as possible. The average is coming out to about 16, 17. So we're right on time. And we'll go ahead and say one thing. I've got this up on the board. Maybe I'll go ahead and draw it because I'm recording. But the homework, which is due on Wednesday, you got a couple days. For number 7, make sure that you're giving your answer theta in degrees. Make sure for number 7 to give that theta in degrees. For number 10, give me your answer in miles per hour. And yeah, I got a text message. On number 12, I'll go ahead and tell you, while there's different ways to solve it, I went ahead and used a system. Okay, because what it's talking about is, you ever worked with one of those or played with those tracks for like the slot cars? Okay, things like that, the curved pieces. That's what this represents right here. Okay, the problem wants to know what's the uniform width of each of those slot pieces. So I said that the outside curve was S sub 2, the inside was S sub 1. X is what you're looking for. Okay, here's the radius with the angle created. Now, I'm not giving you theta. You should be able to figure out theta pretty easily from the problem, but I thought I'd go ahead and give everybody the same advantage if you didn't know quite how to start the problem. Okay, but I solved number 12 using a system. All right, in fact, let me go ahead and do that up here for number 7 on the homework. We want theta in degrees. For, what was it, number 10, we want the final answer in miles per hour. And then for number 12, I used a system. Okay, so this right here is the uniform length you're looking for, the outer arc, S sub 2, S sub 1. This is not going to be a good diagram, but it's okay. And then we have the radius right here. Okay. All right. So I'm going to go ahead and take care of those happy minute grades the first round, get them in. I'm going to try to pass them back to you, because we're going to be doing the exact same thing tomorrow morning. And then most likely, even by the end of this week, I'll probably go ahead and start giving you some type of triangle, and then you'll evaluate, find all 6 trig functions based on the triangle lengths that you're given. So we do need to know those ratios. All right, questions? Okay, then go for it. Help each other out.